Welcome to solverfy.
So for part A, the impedance, we can first solve the inductive reactance. This would be 2 pi times the frequency we know to be 500 hertz. And then the inductance we know to be 150 microhenries, so 150 times 10 to the negative 6th henries. And the inductive reactance is equaling to 0.471 ohms. We know that then the capacitive reactance would be equaling 1 over 2 pi times the frequency of 500 hertz multiplied by the capacitance of 25 nanofarads, or 25 times 10 to the negative 9th farads. And so the capacitive reactance would be equaling to 12,738.85 ohms. And we can then say that the impedance Z would be equaling the resistance squared, so 1 kiloohm or 1,000 ohms, quantity squared, plus the difference between the inductive reactance, 0.471 ohms, minus the capacitive reactance, 12,738.85 ohms. This difference will be squared, and then this sum of the squares will be raised to the 1/2 power. And we find that the impedance is equaling essentially 12,771.13 ohms. Or we can say that this would be equaling to 12.7 kiloohms. So this would be our answer for part A, rounded to 3 significant figures. And then we're doing the exact same thing for part B, except the frequency is now, instead of 500 hertz, 7.5 kilohertz. So this would be equaling 2 pi times the frequency of 7,500 hertz, so 7.5 kilohertz, multiplied by, again, 150 times 10 to the negative 6 henries. And so that we find the inductive reactance to be 7.065 ohms. We know that the capacitive reactance would be equaling 1 over 2 pi multiplied by 7,500 hertz. And this would be multiplied by 25 nanofarads, 25 times 10 to the negative 9th farads. And the capacitive reactance is 849.617 ohms. So the impedance then would be equaling, again, 1,000 ohms squared, the resistance squared, plus 7.065 ohms minus 849.617 ohms, quantity squared, all raised to the 1/2 power. The impedance is then found to be equaling 1,307.59 ohms, or we can say approximately 1.307 times 10 to the third ohms, or 1.31 ohms. This would be the impedance, of course, rounded to 3 significant figures. For part C, the root mean squared current would be equaling the root mean squared voltage divided by the impedance. And so this would be equaling 408 volts divided by 12.731 times 10 to the third ohms. And we find that the root mean squared current would be 0.032 amps. Again, this would be for 500 hertz. And then the root mean squared current would be, again, 408 volts divided by 1.307 times 10 to the third ohms. And this is equaling 0.312 amps. This is at 7,500 hertz. So these would be our two answers for part C. For part D, we want to find the resonant frequency. The resonant frequency would be equaling 1 over 2 pi times the square root between the product of the inductance and the capacitance. So the resonant frequency is equaling 1 over 2 pi times the square root of the inductance. We know to be 150 microhenries, or 150 times 10 to the negative 6 henries, times the capacitance of 25 nanofarads, 25 times 10 to the negative 9th farads. And we find that the resonant frequency is 82.2 hertz. This would be our final answer for the resonant frequency. And then we can say for part E, at the resonance where the inductive reactance equals X sub R, the reactive, X sub R, we can say that then the value of Z is equal to the resistance that is R. My apologies. This would be X sub C. So when the inductive reactance is equaling the capacitive reactance, therefore the impedance is simply equal to the resistance that they give us. And so here, for part E, the root mean squared current is equaling the root mean squared voltage divided by R, the resistance. This would be equaling 408 volts divided by 1 kiloohm, or 1,000 ohms. And this is equaling 0.408 amps. So the RMS current at resonance would be 0.408 amps. That would be our answer for part E. That is the end of the solution. Thank you for